maybe not so small. We're going to talk about the fluid exchange in the tissues. Now, this thing implies knowledge of the concept of hydrostatic pressure and osmotic pressure. So here's what I'm going to do. I'm going to draw a blood vessel. Okay, so this is the blood vessel, right? Blood in a capillary. And here on the right is tissue. Okay? And we're going to talk about different pressures that are exerted either, listen up, by the blood in the capillary or by extracellular fluid in tissue. So we're going to start with the blood in the capillary. Blood in the capillary it exerts certain degree of pressure, certain pressure on the walls of the capillary. Do you agree with me? We know that. So this pressure is called capillary hydrostatic pressure, HPC. Okay? Does that make sense? At the same time, the protein albumin found in abundance in the plasma. As a solute, it draws fluid from the tissue into the blood. Does that make sense? Remember osmosis? The concept of osmosis when, a solute draws fluid towards itself. Okay? So I'm going to put like here, albumin. Albumin draws fluid, pulls it from the tissue into the capillary. So this is called capillary osmotic pressure, OPC. Okay, so far so good? Good? Now what about the other side? What about tissue? Does tissue exert any hydrostatic pressure? The answer is no, because in the normal situation, in non-problematic situation, so to say, all excessive fluid in the tissue immediately drains into the lymphatic system. Okay? So we can say that hydrostatic pressure of interstitial fluid equals 0. Now, we have to appreciate that extracellular fluid, the interstitial fluid, isn't a distilled water. It has some solutes. So it does pull some fluid, some water, out of the capillary. So this is called interstitial osmotic pressure. Are you following me? So here I have 4 components. Well, if we count hydrostatic pressure of the interstitial fluid, we have 4 components. 2 components come from the capillary. Capillary hydrostatic pressure pushes the fluid into the tissue, while capillary osmotic pressure pulls it out of the tissue back in the blood. Hydrostatic pressure from the side of interstitial fluid is 0, and there is a small osmotic pressure that is induced by interstitial fluid that pulls the fluid out of the blood back in the tissue. So based on all these parameters, we can write down an equation for net filtration pressure. Okay? And let's assume that these 2 numbers are positive, right? Is a positive. Just for, so we've got hydrostatic capillary pressure minus capillary osmotic pressure plus interstitial osmotic pressure. And this one is 0. Okay? That makes sense. Now, osmotic pressure exerted by the blood, by the albumin in the blood, is normally in homeostasis, it is constant. Okay? Because the concentration of albumin is constant. Osmotic pressure exerted by interstitial fluid is constant in homeostasis. The only parameter that can be changed here is capillary hydrostatic pressure, which is a blood pressure. Does that make sense? So, let's take a look what happens at the arterial side. So, net filtration pressure at the arterial side, and I'm going to use numbers. So, hydrostatic pressure in the capillaries on the arterial side is 36, I think. 36 or 35. I think 35. I don't remember from the top of my head. Let's say it's 35. Okay, 35. Fine. 35. Okay. We measured it. Osmotic pressure is 27. And osmotic pressure from interstitial fluid is 1. What is the result of this calculation? (35 plus 1 minus 26) gives you, I would say, if I would put like a dollar sign in front of it, that would be no problem. 10. 36 minus 26, right? So you got 10. Units are millimeters of mercury, but that's unimportant. So what about the venous side? Okay. Venous side, the only parameter that is going to change is hydrostatic capillary pressure, which is going to be 17. Now in this case, check this out. You've got 18 minus 26. And it's negative 8. Okay? Now, what does that mean? What does that mean physiologically? Now look. I'm going to wait till you write it down, and then I want you to put okay. Can you all look at me? So this plus 10 means that the fluid goes from the capillary into the tissue at the arterial end, arterial side. We're clear. And then fluid returns back at the venular side. But you see that this net filtration pressure at the arterial side and net filtration pressure at the venous side, they aren't the same. Or they aren't. Which means, and it's really important, not all the fluid that leaves your blood on the arterial side returns back onto the venular side. Does that make sense to you or not? And why is this important? It means that those quote-unquote 2 millimeters that are not coming back, they basically wash the cells in the tissue, removing all the debris and the cells and the pathogens, whatever. And then all those 2 millimeters drain into the lymphatic system. Does that make sense? So it's kind of a cool thing that all your tissues are constantly washed by those 2 millimeters of fluid that are produced due to the difference between the arterial and the venous side. Okay? Does that make sense? Now, here's some things that that I would like to explore with you, kind of, sort of. So imagine that we're going to increase the concentration of albumin in the blood, okay? Let's say you are dehydrated, okay? Are you following me? You're dehydrated. So albumin concentration increases. And as albumin concentration increases, osmotic pressure increases as well, right? So what's going to happen here? 35 minus 27, for example, plus 1 equals now 9 millimeters of mercury. Now here, you have 17 minus 27 plus 1 equals negative 9. Now, what does that mean? Look, it means, check this out, that all the fluid that left your capillaries and went into the tissue, right, returned back. Are you following me? So your tissue, like the way you look now, is partially due to the fact that you have some fluid going into the tissue. If it doesn't go there anymore, you're like drying out. Okay, not literally, but figuratively, your tissues are very dehydrated. Okay, now what's going to happen if instead of playing with albumin concentration, we will increase hydrostatic pressure? Now, let's see. So you go from 35 to 36 here, which gives you 11 millimeters of mercury. And here you go from 17 to 18. I increase it by 1, like just a slightly tad increase, okay? So go 18 minus 27 plus 1, and it gives you negative, why 27? It's going to be 26. It's going to be 26. Okay, 26. So we've got negative 7. Are you following me? No? Yes? So basically, in this example, I changed osmotic pressure. In the next example, I changed hydrostatic pressure. So what actually means, look at this, 36, 18. The difference now is not 2 millimeters of mercury, but 4. Okay, good? And actually, the more you're going to increase the hydrostatic pressure, the more the difference is going to be. You're following me? And at some point, you're going to have, I don't know, like 12 and 6. It means that 6 millimeters are left in tissue. And if not, all of those 6 millimeters can be drained through the lymphatic system. What you're going to have? You're going to have edema. Does that make sense? Are we clear?
What causes edema again? Can you say the last part again?
So think of it this way. The bigger the difference between the net filtration pressure on the arterial side and the venous side, the more fluid remains in tissue. Does that make sense? This fluid will be drained into the lymphatic tissue. But lymphatic tissue, like a sewage, every sewage has a certain capacity. At some point, the amount of fluid that will accumulate in the tissue and the amount of fluid that can drain into the lymphatic system, there will be a mismatch. So you're going to have fluid accumulating in the tissue. Okay? You see that? And people will start developing edema. People with really advanced hypertension, you can see that. Like swollen, especially in the legs, where, and you have to appreciate, when we talk like, oh, this is so standard, this is always 17, this is always 35. No, it's not. It will depend on the local capillary bed. Does that make sense? So basically, think of it this way. In your head, in your arms, in your shoulders, like upper body, drainage The venous return is really easy. It's a gravity. Does that make sense? In your legs, like in your feet, it's the lowest possible point. The venous side, the drainage on the venous side will suck. You see what I'm saying? So this is why, if you like stand for an extended period of time, you don't move around, it's going to happen to your feet, they're going to swell. And if you have hypertension, they're going to swell even more because your venous side doesn't drain as well. Okay? That makes sense? This parameter on your venous side is still pretty high because it's just the blood just remains there. It stays there, increasing the local pressure on the venous side of the capillaries, in the capillary beds, in your lower part of your lower extremities. That make sense?
Can you go over the difference between hydrostatic and osmotic pressure?
Of course. Again, okay. Hydrostatic pressure is, so this one we can basically forget about. Hydrostatic pressure is the pressure due to the flow of blood. That makes sense? Like you increase the pumping capacity or volume, hydrostatic pressure is going to increase. Does that make sense? Osmotic pressure is the ability of a solute to draw water towards itself. Plasma contains a lot of albumin. You see that? This albumin will pull water back into the capillary. I usually say that hydrostatic pressure pushes while osmotic pressure pulls. So hydrostatic capillary pressure pushes the fluid out of the capillary. Osmotic pressure pulls the water back into the capillary. There is a little bit of protein in the interstitial fluid, which will produce some small, very small, osmotic pressure. Does that make sense? So it will pull the water into the tissue. Okay?
Is the osmotic pressure of the capillary competing with drainage from the tissue to the lymphatic system? Like how?
I see what you're saying.
Yeah.
I wouldn't look at it this way. I wouldn't look at osmotic pressure, the capillary osmotic pressure competing with the lymphatic drainage, because I want to say lymphatic drainage is secondary to this whole picture. So the amount of fluid that will essentially enter the lymphatic system becoming lymph is determined by the relationships of these, well, 3 parameters really. So let's say here in this particular situation, do you have anything to drain into the lymphatic system? No, you don't. Does that make sense?
So is the drainage to the lymphatic system like secondary to whatever?
Whatever ends up in the tissue as the result of this balance between the arterial and venous side, whatever ends up in the tissue will eventually drain into the lymphatic system. How much is the question of like, what is your hydrostatic pressure? What is the osmotic pressure?
Okay.
Does that make sense?
Yeah.
Moreover, we can technically imagine the situation when lymphatic drainage is blocked. In some surgeries, surgeons have to repair fragments of the lymphatic system. One of the most common is in patients with breast cancer. the axillary lymph nodes are often, as a result of mastectomy, axillary lymph nodes are removed. And if you know someone who went through radical mastectomy after the breast, with the breast cancer, they often have ipsilateral arm massively swollen, and they have to wear a cuff, which will, so basically the drainage will make this not zero. And in order to so since you can't get the fluid accumulating in the tissue in the lymphatic system, you have to get it somewhere. So you have to exert additional pressure to increase that parameter to move it back into the blood. Does that make sense? Questions? Now, go ahead.
So when someone has a swollen leg or arm, their HP, the number won't be 0.
It won't be. If they have long-standing edema, it won't be. No.
And the reason is because the vas V.
Because for some reason there's no drainage.
Draining.
Go ahead. Say again.
Because the venous isn't draining back into the lymphatic.
Well, drainage into the lymphatic doesn't depend on arterial or venous side. It's a drainage from the tissue. But the swelling, the accumulation of fluid in the tissue will start pushing fluid back in the blood. Okay. Sorry.